started. My name is Matt Thomas, and thank you for tuning in to the USGS Landslide Hazards Seminar. This meeting is hosted by the USGS Landslide Hazards Program and co-organized with contributions from Stephen Slaughter and Jamie Kostelnik. For those of you that are new to this meeting, you have the ability to submit questions via the chat window or to use the raise your hand feature in combination with your microphone or video camera. We're going to wait until the end of today's presentation to take questions. So in the meantime, please just do your best to make sure your microphone is muted and your video camera is off when you're not intending to speak. It's my pleasure today to introduce our speaker, Kate Allstadt. Kate has been a research geophysicist at the USGS Geologic Hazard Science Center in Golden since 2015. She works in both the Landslide Hazards Program and the Earthquake Hazards Program here in Golden, primarily on multidisciplinary studies that incorporate geophysical techniques to study and characterize landslide hazards in earthquake-triggered ground failure. She also leads a project on landslide situational awareness and event response research. Kate, thanks so much for joining us today. I'm going to let you take it away.
All right, thank you, Matt. So let me just get set up here. Okay, so today I'm going to talk about an interesting and unusual landslide that happened in Rocky Mountain National Park about 1.5 years ago. And the work that I'm going to present involves contributions from a wide variety of people. A lot of those names are listed below. And then there's also additional people who provided help and support, especially from the Park Service and some academic colleagues throughout the study. And so we initially got involved in this event when the Park Service asked the USGS for technical assistance. And it made sense, we're located in Golden. This is about an hour and a half drive to the trailhead from our offices. But this event really pulled us in because so many aspects of it were just kind of weird and intriguing. And we kept noticing new bits of evidence, like, we noticed something in some old satellite imagery or in the Eyewitness videos that just kept opening new doors to new lines of investigation and new puzzles to figure out. So that's why I called this the many mysteries of the landslide, because even though, as I'll present it, we figured out some of the mysteries, though not all of them, this event really revealed itself gradually, and it was kind of a nonlinear and fun process to kind of understand what was going on here. So let's jump into it. So what happened? Well, at 4:33 p.m. on June 28th, 2022, at an elevation of 3,600 meters in Rocky Mountain National Park, just a few kilometers up a canyon, accessible from the Bear Lake parking area that many of you are familiar with. At the location of this red star, this happened. So this was caught on video by an eyewitness located down the canyon, and he saw the entire slope starting to move downhill, and you could see that the dust is building up and kind of enveloping the material. And there are actually other eyewitnesses who are located near the toe of the landslide, some climbers in the area, who also captured video footage of the event and just barely escaped. And so they kind of have a harrowing tale of their escape. And so for these reasons, because there's spectacular video footage and kind of, harrowing tale of survival, this received a lot of media attention, especially locally, but some nationwide. So a lot of news outlets covered the story of their escape and the observations from the people who experienced it. There was some scientific interest, such as why the lake downstream turned milky green. There was interest from some networks on the seismic signals that it generated, that I'll talk about. And then there was some grief about the canyon being closed, because this canyon's a really important site for the climbing community. There's famous boulders. It's a huge bouldering destination. And so there was some sadness about some of the boulders being destroyed. One of the eyewitnesses I talked to had a more positive spin on it, where he said that the problems were reset in the landslide. But there was some sadness about the canyon being closed to access for safety reasons. And so we got involved with the goals of helping provide information to the Park Service to help them in their decision making. So primarily we were looking at understanding what happened, what the causes were of the landslide, and then especially in the ongoing hazards related to this slide. So this is kind of a list of the things that we did. So we went into the field about 2 weeks after with some some of the climbing rangers, and we made observations. We had permission to fly a UAV, so we collected UAV video and stills. We also looked at a lot of pre and post-event satellite imagery. We compiled eyewitness reports, interviewed one eyewitness, and looked at a lot of the videos that they took. We also looked at the seismic data and what that could tell us about what happened. And then we used the UAV imagery to make really high resolution DEMs and ortho images that we used for additional analysis and runout modeling. And so we presented kind of our final findings to the park about a year ago, but now a lot of the studies finally public in this paper I have a screenshot of to the right in the journal Landslides. So that's open access and anyone should be able to read that. And then I will note that I'm going to mostly or only talk about the study that we did. There is another group that did almost a completely independent study of this event. So it's kind of interesting to read both papers. We have some similar conclusions. And I'll say that our paper was more observational and they have more modeling. So you can check out that other paper at some point as well. I'm not going to talk about that study today. Okay, so the short version of the story, so I'll just lay it all out there in case some of you drift away or fall asleep, and then we'll get into the details. So essentially, this was a debris slide. So based on the evidence, we don't think that much bedrock was involved, maybe a little tiny bit way up here in the headscarp, but this was mostly debris and it contained permafrost, and we're quite sure about that. And I'll show some evidence for how we know that later on. We calculated the volume to be 2 million cubic meters. Some parts of the slope moved about 245 meters, especially these prominent rock knobs here called the two towers, which will show up throughout the presentation. They moved 245 meters along slope. The maximum thickness, which was below these two towers, was about 80 meters. And then we know from looking back at historical imagery that this slope actually had started moving quite substantially in the 2000s. So sometime between 2000 and 2009, it started to move, and then it really started to accelerate after 2018, which was one of the warmest years on record. And so our conclusions are that the likely trigger for this was permafrost degradation due to warming temperatures, which weakened the slope and increased pore pressures. And then on top of that, it occurred during the spring snowmelt. So there was additional influx of water. Okay, so now for the long version of the story. So I'll start with presenting this unique geologic setting. So here we're looking at a oblique Google Earth image looking up the canyon. So this is a Maxar image from about 2 years before the landslide. And so we're looking up Chaos Canyon. So in the foreground is Lake Hayaha. So this is the lake that turned milky green in that media article that I showed. And so the valley drains into Lake Hayaha. You can see there's not really a clear surface channel. Most of the water flows below these rocks. And then in the background, this is the landslide slope outlined in black. So we'll go look at that closer in a minute. And that is about, the toe of that is about 1.3 kilometers up the canyon from Lake Hayaha. And so between Lake Hayaha and the landslide is the Chaos Canyon Rock Glacier. So this is thought to be a fossil or a relict rock glacier. It may still contain ice, but it's not thought to be moving still. And for this is why there is no surface channel in the canyon, because it's, it's filled with this rock glacier. And so the surface of this is composed of extremely massive boulders. So it's hard to get a sense of that size from Google Earth images. Here's, humans and the same scale as those rocks. So some of them are the size of cars, some are as big as houses. So they're really, really massive rocks. And, it's a good name for this canyon. And you have to climb over these rocks for, a couple of hours to get up to where the landslide is. Okay, so back to our canyon. So along the steep slopes on the side, there is talus mapped, and this is the geologic map by Braddock and Cole from 1970. And so talus is shown in blue, and that includes the landslide slope. They mapped that as talus. The rocks above are silver plume granite and biotite schist. Okay, so now we'll fly up the valley so you can see the character of the Chaos Canyon Rock Glacier and the topography. and we'll fly up to the slope. So this is what the slope looked like about 2 years prior to the landslide. And before we talk about this slope in detail, I just wanted to introduce the same site we just flew over in map view so that you're oriented when we look at maps later. So we just flew from Lake Hayaha in the upper right. We flew over Chaos Canyon, and now we're looking at the slope from around here. So this is the pink is the Chaos Canyon Rock Glacier. The dotted gray is the talus, and then this black outline is the final outline of the final landslide. And so we'll talk about some of the other features on here in a minute. Okay, so back to our oblique view. So you can see that the slope had, signs of instability ahead of time. So again, this is 2 years before the landslide. You can see it has a steep frontal slope that's lighter in color and finer grained, has signs that, rocks frequently move down this slope. And then at the crest of the slope is the two towers that I mentioned before. And this Google Earth map kind of smears them out. So you can see in this photo, which was taken, I believe, in 2019, you can see just how prominent the two towers are. So we can zoom in even further. They really stick out. And then behind the two towers is an area that has a shallower slope. I believe it's about 30 degrees average here. The frontal slope is about 40 degrees average slope, if I remember correctly. And this area was actually mapped it's an unpublished map that the park has in its archives. John Achoof or Akoof mapped this as a rock glacier, but no other rock glacier maps include this slope as a rock glacier. And then I'll just point out before we talk about the rock glacier a little more, there's a perennial snowfield kind of nestled at the top of the slope. This used to persist throughout, it used to last the whole summer, but in some recent summers it had melted entirely away. So back to the rock glacier question. So it is unclear whether this is a rock glacier or not. So it kind of shares some characteristics of rock glaciers in the area. It has a lumpy surface. It has a cirque that can feed snow and debris into it, but it doesn't have other characteristics of, indicating flow like ridges and furrows and things like that. And also the aspect is different. It's facing to the southeast, and most of the rock glaciers in the area faced east or northeast in this area. So it's kind of a puzzling landform. So now let's look at the years leading up to the landslide. So we'll use some satellite images primarily from Maxar. So these are worldview images. So this is about 6 years before the landslide. So we're looking in map view now. You can see the two towers outlined here. And one thing that we noticed early on when we started looking through historical images is that you could see with your bare eye that this slope was moving. So you could see, changes up here, but also the two towers were a really prominent feature that you could see year to year was moving pretty far downslope. And so what we did was a really, really simple version of pixel tracking where we took the two towers in really well orthorectified images that had good view angles, and we just tracked the two towers over time. And this allowed us to go pretty far back to about 1990. So I'll start here 6 years before, and then I'll show the whole time series. There's another view of what the two towers look like. Okay, so this is 5 years later, or 1 year before the landslide. You can see it's moved maybe 15 to 20 meters. But there's some other features in this image that are interesting. So we start to see tensile fractures at the headscarp forming in the snowfield. You can also see that there's a lot of springs coming down from the frontal slope at a range of elevations. And these springs, some of the positions of these persist year to year. You could see these springs a couple of times in some of the available imagery. And some of them, especially this one, have debris flow levees that you can see along the side. So there's definitely a lot of water has been moving through this slope or coming out of the slope. So this image is lower resolution, but it's the closest image we have to the failure itself. So this is now 1 week before. This is a planet image. And you can see that there's a really prominent fracture. The smaller fractures have kind of coalesced into one larger fracture at the top of the slide. And then the two towers have moved since 2016, have moved 53 meters horizontally. So this is substantial movement that was occurring. Nobody was looking for it. The climbers that we talked to, said that they often saw rocks rolling down the front of the slope. They were frequent visitors to the area. So there were, signs of it, but, no one was really looking. And then this is the best post-event image that we have. So you can see that the two towers are now 206 meters down from where they were the week before. The landslide will come back to talk about some of these features in more detail a little bit. So this is the entire time series of the movement of the two towers. So the displacement is shown in red. So you can see that we found a few older images. We're able to go back to 1990 or 1991. And so it started moving somewhere in here, somewhere between like 2000 to 2009. And so it moved, maybe about 10 meters sometime in there. And then it really started to accelerate after 2018, and then it just, really took off. And if we look at the climate data, so we're taking the Bear Lake SNOTEL mean annual air temperature, correcting it for elevation to the elevation of the landslide. So you can see that if we look at the 0 degree line, temperatures started to exceed freezing on average around the middle of the 2000s. There's some years it's below, some above, but that's when it kind of started to regularly exceed freezing. And then 2018, you'll see, that's the warmest year on record, and that's also the point after which the landslide really started to take off. Okay, so now we'll focus in on the day of the landslide itself. And so we actually were able to piece together a lot of different lines of evidence to get a pretty detailed story of what happened that day. We don't usually get this level of detail because there aren't usually eyewitnesses or good seismic records. So I'll start by introducing the seismic data. So seismic data, has extremely precise timing, but it can be difficult because it requires interpretation, and some stations are further away, and you lose information when you get further away. So this plot here is showing the recordings of the main part of the sequence. There's a little bit more that happens that I'll show in a minute. And this is showing data from 3 seismic stations. So we have 3 components of motion, 2 horizontal and 1 vertical for each of these 3 stations that are 30, 56, and 69 kilometers away. Their locations are shown on this map. So the closest station is at MCSU up here, and then the next closest is ISCO. And so I've marked some events here that we'll talk about. So the first one is a possible landslide signal. Then we have, I'll give away the story. This is a blast, but it looks like an earthquake signal. So we'll talk about that a bit. And then we have the main landslide signal. And you can see that it has the character that we expect from landslide seismic signals, where it builds up gradually. It's not impulsive. It builds up gradually, kind of peaks towards the middle, and then gradually tapers out. Whereas this blast has impulsive P&S waves that you can see. Okay, so we're going to use primarily the ISCO station. So even though this was further away, it's actually a better station because it's really high quality. It's located in a cave near Idaho Springs. So we're going to use this time series and kind of correlate it with the eyewitness observations and eyewitness videos. So here is what we were just looking at. This is the ISCO seismic waveforms and the 3 events that were on that past plot. And then I've added this 4th event here that I'll talk about in a minute. Okay, so now we're going to start looking at some eyewitness videos. I talked with one of the eyewitnesses, Jeremy Fullerton, at quite length, and he also shared some videos and the timestamps of those videos. And so we use that information here, and we assume, because they were from cell phones, that they're correct to the closest minute. And then the seismic times are correct within a few seconds. Okay, so let's see if I can get this to work. Okay, so the first thing that we have, actually before this 3 p.m. time, the climbers had noticed when they got there that day that the slope was more active than usual. So as I said, they saw rocks tumbling down it from time to time. They visited the area a lot, but on this day, they noticed that there was more rocks rolling down than usual. Then from about 3 to 3:40 p.m., Jeremy took a series of videos that he shared with me that kind of show a buildup of activity from individual rocks rolling down the slope to this video here, which shows, it'll zoom in a second. You can see there's a lot of rocks rolling down in this one spot. This is taken at 3:36 p.m. And then he'll pan over in a second and you'll see that there are actually rocks rolling down all across this frontal slope, not just in this one spot. There's a really large one. So this indicates that the landslide was starting to slide, at pretty large depth. And then these are, smaller metastable rocks that are adjusting to this, this movement that's starting to happen. So this is about an hour before the main landslide happened. So I'll let the video finish. And there's the two towers up here, so you can kind of get a sense for what they looked like before the failure. Okay, so then the first seismic signal that we can see, these ones are too small to see 30 kilometers away, but the first seismic signal we can see happened about 4:31:13 local time. And this is also when we have a video that some of you may have seen on Instagram by William Mondragon of one of the towers kind of starting to fall into the slope, and then rocks tumbling down the whole front. And then you can see that the whole slope, underneath this shallow stuff, the whole slope is starting to move. So this is kind of this little blip here. So you can see the seismic signal kind of builds up and then dies out again. Then we have this blast signal. So I'll talk about that in a minute and its potential connection to this, but we'll skip that for now. So that was a little less than a minute after that first landslide signal, and then a little more than a minute before the main landslide signal. So now we're at the main landslide signal, which was at 4:33:16. And so we have part of a video. This was part of that compilation on Instagram. But I have the full video, and they actually, the slope, let me see if I can play it again. The slope starts to move towards them. Dust is starting to build, and then they drop the camera and start running. And so Jeremy told me that they just dropped everything and started running. They got enveloped in dust, and then luckily they escaped unharmed in the end. So that's the video caught from in front of the landslide, and we think that it's showing the beginning of this video, which we saw earlier, viewed from down the valley. So you can see the dust is starting to really build up. Here's the two towers starting to slide down. The dust is kind of covering everything, but you can still see the two towers. And it stops kind of abruptly, which is interesting because the seismic signal also stops somewhat abruptly. And so we estimated, using the dimensions of the two towers, we estimated this velocity to be about 5.4 meters per second. So that's about 12 miles per hour. Okay, so that was the main event. So the climbers, they fled and they survived. Luckily, the dust started to clear, but they didn't have any of their stuff. And they had been very close to where the landslide toe ended up. That's where they were climbing at the time. So they went back to get their stuff, very carefully. They had a watch set up, and then had to basically run again because another collapse happened. They said, there was a crack that kind of opened in the displaced towers. And I'll show you what I think the deposits from that are later. But there was this like aftershock signal around 4:42. So that's kind of the timeline. And then if we go back to the blast signal, so this ended up, I gave away the story, this was a blast. But the interesting thing was we didn't know that at the time, and the location of it, the people in our building at the National Earthquake Information Center located it and got a pretty decent location, and it was almost right at the landslide. And so because it was almost right at the landslide and, right in the midst of the sequence, we thought that this signal was probably related to the landslide initially. And so that's one thing that kind of got me really interested in this event, because I do a lot of work with landslide seismology. So we wanted to investigate this more. And the reason that is so exciting to have like a earthquake-like signal where you have, clear P and S waves that indicates an impulsive source, is because it's kind of rare to have that associated with a landslide, but has been observed in some special cases that often involve ice. So I'll just mention why we were interested in that signal. So first of all, there are maybe like a dozen cases or so where there have been repeating earthquakes prior to a big landslide that kind of get closer and closer together. They're thought to be stick slip as the landslide's starting to accelerate and kind of getting stuck and slipping. So this shows a spectrogram, its frequency over time of a landslide in Greenland, and each of these vertical lines is a little earthquake, and you can see they get closer and closer together, and then we have a big landslide that happened. So this was in an area with permafrost, and not all cases have happened in areas with permafrost, but most cases seem to involve ice or permafrost where these happen. It's also interesting to just have a single impulsive signal because it can indicate some sort of brittle failure, something very sudden. And so we've seen impulsive signals before landslide quite a few times actually at Iliamna volcano in Alaska, where there's a glacier that kind of rebuilds and detaches every couple of years and has the same landslide over and over again. And so this is the signal from one of those. So you can see the avalanche signal here gradually builds up, peaks and dies out. But before it, there's this impulsive signal that we think is from that, potentially from that glacier detaching. And so that's why we were interested in this quake and its connection to the landslide. And so we started to look into it more, and we did a repeating earthquake search. So this is where you take the waveform of the earthquake that, the one that happened right before the landslide, and then we kind of scan it against all the other data and try to find matches, like a fingerprint match. And we got really excited because we found a whole bunch. So this is showing just 20 cases. The dots are when we had a decent match. So we got really excited, but then started to look a little closer and noticed, oh, they all happen at about 4:30 p.m. Mountain time. That's interesting. And then also that some of them continued after the landslide. So this is when we started to, make the connection that this actually was not from the landslide. This was something related to human activity. But that was super puzzling because, the landslide happened in a wilderness area. The location seemed to be pretty good, the seismic location. So we explored some options nearby. There's a water tunnel that goes right under the landslide. We're like, oh, maybe a gate was slamming shut or something like that. It wasn't that. We thought, oh, maybe they're working on roads in the park. It wasn't that. We talked to the park. We called all the quarries in the area. So it took a lot of phone calls. But finally, we confirmed the source after talking to the state blasting regulator that this was actually a quarry, or not a quarry, a reservoir construction blast at the Chimney Hollow Reservoir, which is located about 36 kilometers east of the slide. So we confirmed that at that exact time they were doing blasting. So here's a still shot of it. There's some really cool videos you can look up of the blasting that they're doing. It's pretty impressive. Only equivalent to a magnitude 1.4. But it's pretty neat. So what happened was that our location was off because the stations are all north and south of the landslide. There's some other stations too, but the geometry just didn't give us good resolution in the east-west direction. So it wasn't related to the landslide, but it still raises the question of was there any connection? Because it is, it happened really close in time. It happened right after we knew the slide was starting to move and right before the slide really accelerated into a catastrophic failure. And so I did a few quick calculations, and we estimate that the shaking from that blast at the slide was pretty tiny, so 0.001% G. For earthquake triggered landslides, usually it needs to be 2 to 8% G. So this is, a tiny amount of shaking. And we know that the slide was already moving from the Eyewitness video timestamp, so we know that the blast did not cause the landslide. But it is pretty interesting that, this blast happened, tiny ground motions, but the slide was already unstable. So it just is interesting to think about whether a tiny little bit of extra vibrations can change the way that's, something that's already unstable can behave. So we don't know, if that's the case or if this is just a coincidence, but it's kind of interesting to think about. Okay, so back to the landslide. So this is a photo that we took when we were in the field about 2 weeks after the landslide. And so we've annotated a couple of the primary features. So you'll see in the foreground, we have the displaced 2 towers that are now kind of rolled over on their side. Coming down from like a low spot in the two towers, there's this elongated tongue that has these really unusual conical mounds of white and gray debris. So we'll get back to that, but we think that maybe this tongue of material, this might be that last event that the climbers mentioned where they said that crack opened in the two towers. So some of the material might have rolled down between that gap there. So other features you can see are there's some little dots of where melting icy debris is located. And then you can see on the south side of the slide, there's this kind of separate channel that had active debris flows going down. And I think we saw maybe, I think it was 2 or 3 debris flows happen while we were there in just a few hours, and lots of individual rocks coming down here. And the snowfield was up here, and a lot of this was because that snow, was still up here, was melting, and was kind of sending debris flows down this channel. And there was this almost like a dam of big boulders of snow, really dirty snow, and mud and debris was building up behind it and kind of breaching the dam occasionally and then flowing down the front. And then I think, I'll just mention that the toe of the landslide is still pretty steep. It was about 35 degrees, on average across the front of the slope. So it's still pretty steep, pretty unstable, but most of the activity when we were there was on this left side. We didn't really see anything happen on this, the right side where it was drier. Okay, so here's some of the drone footage. You can look at all of this yourself. So we're flying, it kind of jumps a little bit. Maybe I'll show this twice. This is looking in that wet area the debris flows are coming from right now in the headscarp. This is the snow boulder dam that I was just mentioning. And then this is looking down some of those debris flow channels. Let me see if I can play it again. Because the first part, let's see. Turn that off. Okay, so now we're looking, here's the displaced two towers. And you can see the snow boulders on the left, and then I'll let you look at this part again. That's the headscarp on the south side. There's the snow boulders and the debris flow channels just on the other side, and then this is looking down some of the debris flow channels. So you can download all of this imagery and the results of it, like the high-res DEM and ortho image, from this data release on Sciencebase. So this is also referenced in the paper if you need the link to it. Okay, so we used that 3D DEM along with a 1 meter LiDAR image that was taken, I believe, in 2020 to estimate the elevation changes and estimate the volume of the landslide. And so this plot at the left shows the elevation difference. So that's just subtracting one DEM from the other. But the material did not completely evacuate the source area. So we had to estimate the sliding plane to get the volume estimate. And so this is showing we fit log spirals to where there was exposed, exposures of the bedrock and also the pre-event sliding surface. And then we were able to separate the elevate or the thickness distribution of the source material and the deposits. So that's in the center and the right. So you can see the source thickness was up to 80 meters thick right below the two towers. We estimated 2.13 million cubic meters from the source material. And then the deposits were more spread out, about 54 meters thick at the maximum, and that's towards the front of the toe. And we estimated about 2.09 million cubic meters. So pretty similar between the source and the deposit thickness, and there's some uncertainty there. This is a really detailed structure map that Jeff Coe did using the DEM and the ortho image that shows some of the interesting features that were visible on July 15th. So you can see there's a lot of seeps, these little blue circles. That's where we think it was melting permafrost in many cases. On the north edge, you can see there's some internal scarps showing that there's internal deformation within the slide. Here's showing all the debris flow channels, debris flow deposits. This is that dam of snow boulders, and then there were more debris flow deposits down here. And then one interesting thing that we'll come back to in a second are these yellow and teal blobs. So they're in a band, maybe like 70 meters wide behind the two towers. And these are actually blocks of debris that was frozen and is now in a mound shape, or debris that's still frozen and you could still see was melting. So I'll come back to that in a second, but I just want to mention this wedge of debris that was remaining, you know, the edge of it is where we see these seeps coming out from. The material was removed. So this is one area there might be risk of additional material coming down. This is a photo from a few months after the landslide. A friend of a colleague took, and you can see there's a little bit of a fracture at the top of it. It was there before, but we don't know if the fracture widened or not. So that's about, you know, the volume could be somewhere from 100,000 to 300,000 cubic meters. Okay, so now let's go back to the permafrost evidence. So what we have here is, this is a satellite image at the left from 4 days after the landslide, July 2nd. And then this is that image from the UAV taken about 17 days after the landslide. And so you can see in July 2nd, all these teal blocks are blocks of frozen icy debris. We'll zoom in and look in a minute. And then, you know, about 2 weeks later, those melted super fast, and now they're mounds of debris, most of them. There's a few that are still frozen. So melting happened really fast. And you can see that those white mounds that I pointed out, you know, also were more frozen early on and then melted by the time we were in the field, except there was a kind of a core that was still there that I'll show. So this is zooming in this area here. So this is 4 days after the slide. So you can see they look like rocks, but they kind of have dark rings around them, which indicates melting. And then if you look at the same spot 2 weeks later, they're gone. There's no more rocks. They melted into these mounds of debris. So that's pretty clear permafrost evidence, but we have even more compelling evidence actually from one of the Eyewitness videos. So this one was taken 24 minutes after the slide. So this was, you know, this was after all of those events that I showed in the timeline. And you can see these are the two towers that collapsed. This is that little tongue that went down from the center of it. And you can see these two boulders here. They look like rocks. But they have a stripe on them. There's a white stripe and a gray area. Same with this one. It's a little less prominent. And then if we look from a similar angle 2 weeks later when we were there in the field, that is where these two conical mounds are. And you can actually see the same pattern of gray, especially in this one. See the dark gray and the white color. The same pattern of striping, but they've melted into these conical mounds. They're called mollards. They kind of have a chimney of material that was still frozen. There's one right here you could see sticking up. So this is mollard formation in action. So mollards are, you know, have long been recognized as a likely signal that the blocks originally were permafrost when they failed in a landslide. But this is actual, you know, observations of it being frozen in a block and then melted in a conical mound. So that's pretty cool. So just kind of putting this in bigger picture and historical context, this is a pretty unusual event for Colorado and also in general. So it was at really high altitude, and it was a rapid slide in icy debris. It's pretty unusual for a debris slide sourced in debris to be this large. We had a lot of trouble finding any other examples. The examples that we did find, you know, many of them started as primarily rock. But most debris slides in the literature also, you know, kind of became an avalanche or a flow, became more of a granular flow, and this did not. And that is likely, at least in part, because it encountered that extremely coarse rock glacier, the Chaos Canyon Rock Glacier, in its runout path. And this slide, maybe also for the same or similar reason, has pretty low mobility for its size. And so we looked in the literature to try to find, you know, other examples of this. You know, we wanted to use that to, like, you know, help guide some runout modeling to understand how far additional failures might go. And we were not able to find many, if any, historical landslides like it. You know, there's a couple examples in Greenland and Iceland that were sourced in frozen debris, but they were a lot more mobile. And there were some rock glaciers that had collapses, but it wasn't the whole thing. You know, it was maybe part of the rock glacier, and most of those were finer grained rock glaciers than what we're looking at here. So if anyone knows of examples like this, let me know, but we didn't really find any. So it's kind of an unusual special event. Maybe we can look at the mobility of this landslide in a little more detail. I think a lot of you are familiar with mobility index H/L for landslides. You measure from the top of the landslide to the toe of the deposits. That's the H/L, or the tangent of that angle is equal to the H/L. And so there's a lot of different ways of referring to this, like travel distance angle, Heim's angle, reach angle, and it's kind of an imperfect proxy for the apparent angle of friction in some cases. So we wanted to compare this landslide to other similar events, and it was pretty hard to find a compilation of mobility measurements that was appropriate. The closest we found was this one from Hayashi and Seed, 1992, of non-volcanic subaerial landslides. You know, a lot of compilations include volcanic landslides, and they are a lot more mobile than non-volcanic ones. And so here we're comparing, this is their data set. This is their regression equation between volume and mobility. This is where the landslide, the Chaos Canyon landslide falls. But actually our H/L measurement was 0.54 or 28-degree reach angle. So that's a little bit above the 95% range for that size. And the H/L of the center of mass, which some say is, you know, a closer estimate of the apparent angle of friction, that was about 30 degrees. Or 0.57. And actually, interestingly, I'm not going to have time to show it. We did model the main landslide, and we got the best fit to the deposits using this about 30-degree friction angle for the modeling. Okay, so we're getting close on time, so I'll touch on this, but I won't go into too much detail. But one thing that was of interest was, you know, what is the ongoing hazard at the site? You know, in terms of, you know, in terms of public safety, you know, where additional failures could happen, when they might happen, and so on. So we spent a decent amount of time kind of pulling together the best information we could about this. And so there's some, you know, common sense things like, you know, the hazard of additional movement is likely highest during the spring snowmelts after intense summer storms. You know, major sources of material would be the deposits themselves remobilizing. Remember, they're still at a 35-degree angle at the front of the slope. We don't know what's inside the slope. We don't know, you know, if there's permafrost that's continuing to melt, or, you know, what kind of materials inside there. So there's always a possibility of remobilization of the deposits that already failed. There's also, you know, additional debris that could fail from above, like I showed from that wedge, and then, you know, around the other sides of the headscarp as well. So that's where that wedge is. And then most post-event activity, you know, we put together this slide, you know, about a year ago, but it still holds true if you look at the imagery today, that most of the post-event activity has been along the west or the southwest side of the slide. So in this debris flow channel. So now if you look at, you know, some of the imagery after the summer, there's, you know, a bigger debris flow fan here, and then there's a pond over here that's kind of got a little delta forming in it. So most of the activity has been along this west or south side. Most concerning scenarios for stability would be a rain on snow event, you know, following a winter with a high snowpack, which could introduce more water into the deposits, or rapid melting of a high snowpack if there's a really warm period in the spring. But we don't think that this is a very mobile environment for several reasons. You know, one is the obvious, that the runout path is a rock glacier, the surface of which is, you know, enormous boulders that would be very difficult to entrain and liquefy. You know, that's a big source of mobility for some landslides. It's probably not going to happen here. And there's also not a well-developed surface channel for flows to become channelized in. And there's also a lot of local depressions where the material can kind of, if it fails, can kind of sink locally rather than, you know, continuing down slope. So I'll show that in a simulation in a second. But there is a lot of uncertainty here. You know, there could be finer grain material in the deposits. Those white blocks, we don't know what they are. That's one of the mysteries that remains. We don't know what that white material is. There's definitely rock flour, that's been washing down and turning the lake downstream green. So there could be finer grain material within the deposits. We don't know what's in there. It's also possible, that more mobile flows could occur. The permafrost blocks that are in here could have been broken up. There's more conduits for air and water to flow in. So, additional flows could be more mobile than this past flow was. And there just aren't really good examples in the historical record of events like this. Okay, so we did some simple simulations. I won't spend too much time on this, just to kind of see, how far, in a worst case scenario, if the entirety of the deposits remobilized, how far would it be reasonable for them to go? And so we used a shell top granular flow model with a simple Coulomb rheology, just a single constant friction angle. We very conservative in assuming the entirety of the deposits were remobilized. We were not conservative in assuming there would be no entrainment or liquefaction, but that's reasonable in this setting. And what we did was we used the H/L ratio of historical data from that Hayashi and seed data set, and used that as the friction angle for simulations. And we modeled a 95% range of that. And the reason that we did this is because the study by Lucas et al. Used shell top and found that that H/L ratio was a pretty good approximation of the friction angle with this exact model that we were using when slides were larger than 1 million cubic meters. And then we also looked at some more conservative approaches, as in more mobile. I'll show one simulation from that. I don't think it's very realistic, but we'll show it. So this was our best estimate of the deposits remobilizing. So this is at the mean H/L used as the friction angle for Hayashi and seeds data set. And so you can see that it doesn't go very much further than it already did. There's a depression over here. That's kind of a sink for a lot of the material, a little depression over here. And one area the park was concerned about was the meadow, because climbers congregate in this area. So there was concerns that, flows could go down this area here and reach the meadow. So in the mean scenario, that doesn't happen. This is the most mobile of our estimates. So in this one, it maybe just barely approaches the meadow, but still most of the material gets caught in this sink up here of this depression. So those are kind of what we think are most realistic cases. If we modeled it as a debris flow, and this is I don't think this is very realistic, but we took the mean value from a debris flow data set by Correlated et al. And that gives you a lot higher mobility. It reaches, almost all the way to Lake Hayaha. But this is, like I said, probably, pretty unlikely situation. Okay, so I think I'll end there, and that'll leave a little bit of time for questions. So again, this was a pretty unusual landslide for Colorado, and actually maybe in general as well. High altitude is pretty large, entirely in debris, and the debris contained permafrost. And I showed, that there was a gradual buildup to the main failure event, the day that it occurred, but also in the decades beforehand. About 2 decades before, we know that had started moving, and it seems to be related to the temperatures, the air temperatures at the location of the landslide starting to exceed freezing on average. And then, this has a lot of implications for other similar slopes in the park and also in Colorado. We didn't broaden our investigation to see if other slopes are moving, and we just weren't looking at it. It's very possible. So there's a lot of work that could be done there. And there's still a lot of mysteries just with this one slope to investigate, like what is that white material in those blocks? What's inside the landslide? Even things like what is the origin of the Chaos Canyon rock glacier? That surprisingly I couldn't really find information on. It's possible, there's kind of a landslide scarp above where the landslide happened in 2022, like was the Chaos Canyon rock glacier related to a landslide? There's just a lot of interesting things going on at this site. So I think there's still a lot more work to do. So with that, I will wrap up and take some questions.